Everybody, welcome back to chemistry. So what I'm going to be talking about now is something called covalent bond energies and how these can be used to find the changes of enthalpies of reactions, and I'll talk a little bit about bond lengths. So one of the things you probably have seen is when you were drawing Lewis structures is that you can have atoms bonded together in several different ways. So oftentimes you have atoms bonded together with a single bond. Sometimes you have a double bond, sometimes you have a triple bond. And so what you'll find is that you'll need different amounts of energies to break those bonds. And so I need to sort of talk about that and how to use that information to figure out the change of enthalpy of chemical reactions. So before we start doing that, let me just kind of make some summary points here. Okay, so the first summary point is this. Let's say you have atom X, and it's just kind of flying around in space. Let's see if I can get a better pen here. So here is atom X. Yeah, that's a good pen. And let's say there's atom Y, and they're out here in space. So either these are the same atoms, the same kind of atoms, or there could be different atoms, for example. And so let's say you somehow promote conditions so that they bind together. And so they will bind together like this. Okay, and then basically what has happened is you have formed a bond between atoms X and Y. So what I want to talk about is the energy changes that go on when such a process happens. And so one of the things that is kind of a fact that you should know is that if you sort of have atoms separated in space, they tend to be considered to have high potential energy. However, when you bring those atoms together and they bond together, that really stabilizes them quite a bit. And so the reason why that stabilizes them is oftentimes that when they bond together, the electron configurations change such that they get noble gas configurations. That can be done with ionic bonds, and also that can be done with covalent bonds. And so when you bring atoms together, they get a lower potential energy. So if you have atoms out in space, they have a lot of energy, and then when they bond together, they'll have less energy. Something has to happen to that extra energy that these free atoms have, and that is just released into space. So to finish this off, I'm just going to point out here is that when you have atoms forming a bond to form a molecule, energy is released, and so this is considered basically an exothermic process. And this is pretty much true for all atoms. Doesn't matter what kind of atoms you have. Any kind of atoms that you bring together and they stick together to form a bond, to form a molecule, this will release energy into space, and this will be considered an exothermic process. And so there are some signs that we can associate with this process. And so, for example, if you're considering the enthalpy change in this process, delta H here, because it's an exothermic process, it'd be negative. And because it's exothermic, you're basically releasing heat out into the environment. So Q will be negative as well. Okay, so now let's take the reverse process and see what happens. Let's say you have two atoms bonded together, X and Y. These two atoms could be the same atoms, or they could be different atoms. And let's say that you have them together and then somehow you break them apart. And you break them apart and you release the free atoms into space, X and Y. So if you bring free atoms together to form a molecule and that releases energy, what do you think is going to happen is if you have the molecule and you release the free atoms, is that going to release energy or is that going to require energy? And I think what you're going to see is because this is the opposite process of this here, it's going to require energies here. So it's going to be energy is required. And so this is an endothermic process. And so it doesn't really matter what kind of molecule you'll have. Any different kinds of atoms bound together in this molecule, you're always going to need to add energy to that molecule to separate the atoms. And the reason is because the molecule has low potential energy and these free atoms have high potential energy. And so you're going to have to add energy to this molecule to get the higher potential energy free atoms. Okay, so what are some signs that are associated with this process? So for this process here, where we're taking some kind of molecule, we're busting it up into free atoms, this change of enthalpy, as you can see, requires energy, and so this is associated with a positive sign. And so Q, the heat involved, is a positive sign, which indicates, again, that this is an endothermic process and energy must be added to the reactants to get the products. Okay, so what we're going to do is we're going to focus on some of the quantitative details of the energy required to break a bond between atoms to separate the atoms into free space. And this energy that is required to do this is called bond energy. And some books call it something else. They call it slightly different. They call it bond dissociation energy. And these are basically the same thing. So I think the reason why it's also called bond dissociation energy, because basically it's the energy required to dissociate these atoms in the molecule into free separate atoms in space. Okay, so what I want to do now is kind of look at some of the numbers involved in this. So we'll bring up the next slide. And so, for example, if you have the diatomic hydrogen molecule and you add energy to it and break that into hydrogen atoms, that's going to require 436.4 kilojoules per mole of energy. So it will require that energy, so it's going to be an endothermic process. Now, similar values for chlorine. If you have diatomic chlorine and you add a certain amount of energy to that, it will break the molecule into atoms. It just requires a different amount of energy to do so. With HCl, which is hydrochloric acid, you can take that molecule and bust it into the hydrogen and chlorine atoms, and it requires a different amount of energy to do that. Now, let's compare these molecules to the next one, oxygen. So oxygen, O2, I think what you can see is it requires more energy to break the two oxygen atoms and separate them into the space than the other ones we previously talked about. And there's a very specific reason for this, and the reason is this. You might remember the Lewis structure of diatomic hydrogen. You will remember that it had one single bond. If you look at the Lewis structure of diatomic chlorine, it also has one single bond. Hydrogen chloride also has one single bond, and so you need some energy to break that single bond to release the atoms. But with oxygen, if you look at the Lewis structure, what you'll notice is it has a double bond. And so if you have a double bond, you might expect that you might need more energy to break that double bond to release the oxygen atoms. And so here, look at nitrogen. So nitrogen, diatomic nitrogen, requires even more energy to bust it up into nitrogen atoms, 941.4 kilojoules per mole. And so why would that be? Well, you can maybe get an answer by looking at the Lewis structure, and you'll see that diatomic nitrogen has a triple bond. And so you're going to need even more energy to break up the diatomic nitrogen with its triple bond, more energy needed to break up a triple bond to separate the nitrogen atoms. So in general, the trend you should know is that when you're thinking about the amount of energy required to break a bond to separate out the atoms, the energy required is relatively low for molecules with a single bond, a little bit higher for molecules with a double bond, and the highest for molecules with a triple bond. So that's something you should definitely know. Okay, so one question to ask is, how is it that these bond energies, these energies needed to break a molecule and separate into its atoms, how are they measured? Okay, so I'm going to kind of refer here to the screen here, and so I'm going to make some notes here. So one thing I want you to notice here is I have a table of bond energies, and so the first bond energy I have is for the energy to break diatomic hydrogen, and so it's 436 kilojoules per mole. And so the next one is for breaking a bond between hydrogen and carbon, which is a single bond, and it's about 414 kilojoules per mole. And so they're not too far off from each other because they're both single bonds. But here's the thing, when you look at this chart, it's good to kind of keep in the back of your mind that for some of these molecules, you can measure experimentally how much energy it requires to break the molecule, bust it into its atoms. So that is true for diatomic hydrogen. Now, how about the bond between hydrogen and carbon? Can you measure experimentally what the bond energy is between hydrogen and carbon? And the answer is no, is because there really does not exist a diatomic molecule, in other words, a molecule of two atoms, that only has carbon and hydrogen bound with a single bond. It just doesn't exist. So how do they get that value? They can't do it by experiment. What they do is they look at experiments with other molecules that contain these carbon-hydrogen bonds, and somehow through mathematics they sort of infer what they think the average carbon-hydrogen bond energy is going to be. And so they think it's going to be about 414 kilojoules per mole. So again, this is not an experimentally determined value. This is a value that was determined as an average from looking at the experiments of other molecules. So like you may have one molecule that has CH bonds, but their bond energy is like maybe 450 kilojoules per mole. You may have another molecule with CH bonds. It's a different molecule. CH bonds are there, but in a different molecule, and they may have different values. It may be something like 423 kilojoules per mole. So keep in mind that for the ones that are not determined experimentally, these are average values. Okay, so now let's start looking at trends of bond energies. And so one of the trends I just kind of mentioned is really clearly seen again here when we're looking at actual numbers. And so what you can see in that top red box, they were able to somehow calculate what they think the energy would be needed to take a carbon-carbon single bond and to break that. And it would require 347 kilojoules per mole. And what you can see is that if you have two bonds, it's going to be a larger energy. If it's three bonds, it's going to be higher energy than that. So again, that sort of confirms the idea is that when you increase the number of bonds between atoms, it requires more energy to break them. Now, you can change the atoms around. Look at the next box. Now we're no longer at carbon bound to carbon, it's carbon bound to nitrogen, and you see the same trend. And also carbon bound to oxygen, you see exactly the same trend in that carbon singly bound to oxygen has a relatively low bond energy at 360 kilojoules per mole, but look at the carbon triple bond oxygen. That requires a lot of energy to break that bond at 1,072 kilojoules per mole. And then you can sort of look at the nitrogen series as well. Okay, so one of the things you're going to have to do is you're going to have to look at a table of bond energies and calculate what the change of enthalpy is for a chemical reaction based on the values of bond energies you see in the table. So I have some notes on how to do this here, but I think I'll just go over sort of an example problem. But just to point out, you might remember in 109 that we calculated the change of enthalpy for chemical reactions in a number of ways. And so one way we did it is by looking at data we might get from a calorimeter. And so we did several problems regarding that. And so also another way we looked at it is by using Hess's law. So you might recall that there we had several chemical equations and that maybe we would flip the equations over and then maybe multiply with multiples to get terms to cancel out so that we could get a final equation that we wanted and get the change of enthalpy for that equation. And then there was another way that you did it by looking at the heats of formation of the compounds that are in the chemical reaction. Now we're going to do it in a fourth way. The fourth way here is we're going to calculate the change of enthalpy of a reaction by looking at bond energies. And so the key formula to do that is that the change of enthalpy for a reaction is going to be equal to the summation of all the bond energies in the reactants that for all the bonds that are going to be broken minus the summation of all the bond energies in the products of all the bonds that are going to be formed in the products. So let me just do one example here, which I've kind of in part written out in this slide. So what I want you to notice here is that here we're looking at a particular reaction. We're looking at hydrogen gas, which is diatomic hydrogen, reacting with fluorine gas, diatomic fluorine, producing two molecules of hydrogen fluoride. And so the question is, can we use bond energies to calculate an enthalpy change for this reaction? The answer is yes. And so what I have there is I have listed the bond enthalpies for each of these molecules. So Diatomic hydrogen has a bond enthalpy of 436 kilojoules per mole, and there's a value there for diatomic fluorine and for hydrogen fluoride. So there I have sort of a calculation that I can use to work out the change of the enthalpy of the reaction. But let me kind of write a little bit more about that. So what we have is hydrogen reacting with fluorine, and they're both in diatomic states, and we're getting hydrogen fluoride, and I'm balancing the equation by putting a 2 in front of there. And so what I want to do is calculate the enthalpy change of the reaction using bond energy data. So one thing that helps me do this, so I'm less likely to make a mistake, is before I actually do the math of figuring out what bond energies I need, what I'm going to do is I'm just going to draw Lewis structures for each of these molecules. So when I draw the Lewis structure for diatomic hydrogen, I would write H single bond to H. And so that tells me that I need to look up a bond energy for hydrogen bound together by a single bond. And so with fluorine, this is its Lewis structure. And this reminds me that I need to look up a bond energy for fluorine molecule that has a single bond between the fluorine atoms. And then how about hydrogen fluoride? It looks like this. So this reminds me that I need to look up a bond energy of hydrogen bound to fluorine. Okay, so now I think this is enough information where I can sort of hopefully correctly solve this problem. So what you'll note is that the change of enthalpy of the reaction is going to be equal to the sum of the bond energies of the reactants minus the sum of the bond energies of the products. Okay, so one thing to sort of keep in the back of your mind is when we're converting diatomic hydrogen fluorine to 2 molecules of hydrogen fluoride, think about which bonds are being broken and which bonds are being formed. So we're going from these reactants to this product. So what must happen is that the bonds between the hydrogen atoms and the fluorine atoms must be broken. Then the atoms rearrange, and then we reform 2 hydrogen fluorine bonds in the product. So that's something to keep in mind. We're going to break the reactant bonds and we're going to reform new bonds in the products. So here we're going to be looking into the energies that break these bonds, and we're going to be looking at the energies when these bonds are formed. And basically when you put these energies from the bond energy table in this equation, that should give you a good enthalpy change for the reaction. So what I'm going to do is work that out. So let's look at the reactants. So let's look up the bond enthalpy for diatomic hydrogen. I have a value there, is 436. I'm going to leave out the units. And so I need one of these bond enthalpies. How about for diatomic fluorine? I have in that table there, it's 159 kilojoules per mole. I'm just going to leave out the units there. We have one of those bond enthalpies. And so these will be added to give me the total energy needed to break the bonds in the reactants. And so now we're going to subtract the bond enthalpies of the products. And so be careful here. We need to look up the bond enthalpy, or excuse me, the bond energy for hydrogen fluoride here. And so the bond energy for hydrogen fluoride is 565 kilojoules per mole. We're going to leave out the units, and we need 2 of those. So anyway, if you add up 436 plus 159 and you subtract from it 2 times 565, what you should get in the end is this number here, which is negative 535. And this is going to be kilojoules. And so what does this mean? What this means is that when you have the reaction of diatomic hydrogen reacting with diatomic fluorine to produce 2 hydrogen fluoride, it's a negative value, so it's a very exothermic reaction, and it has 535 kilojoules. Okay, so what I'm going to do now is I'm going to do a more complicated one. So I'm going to do the first one here on the top of the screen. And so we have CH4, which is methane. plus diatomic chlorine gives us the products of CH3Cl, which is methyl chloride, plus hydrochloric acid. Okay, so what we want to do is calculate a change of enthalpy of this reaction using bond enthalpies. Okay, so again, I might suggest first writing Lewis structures of these molecules so you can identify the kinds of bonds that are being broken and formed. So methane is pretty simple Lewis structure, carbon in the center, surrounded by hydrogens. They're all singly bonded to carbon. Diatomic chlorine is this. Oh, there we go. Okay, I'm just adding lone pairs, real pain. So there's diatomic chlorine. Okay, methyl chloride, be careful here. So we have a carbon in the center, and there are 3 single bonds to hydrogen, and a single bond to chlorine. And then HCl is going to have a single bond from H to Cl. Okay, so what we want to do is calculate the enthalpy change of this reaction. So the change of enthalpy for this reaction is going to be the sum of the bond energies of the reactants minus the sum of the bond energies of the products. Okay, so we have to figure out the bonds that are being broken in the reactants, and we have to make sure we know the correct number of them, and then we'll look up their values in the table. We also need to know the kinds of bonds that are being formed in the products, and we have to know the number of those bonds that are being formed and look up their values in the table. So let's go ahead and go through this process. Again, we need all the bonds here that are going to be broken into these reactants. And so when you have this reaction here, you're going to have to break each one of these carbon-hydrogen bonds. So we have carbon and hydrogen bonds, and we have 4 of them we're going to have to break. So we'll have to take the bond energy of carbon and hydrogen and multiply it by 4. Here we only have 1 chlorine-chlorine bond, so here it's 1. Chlorine bound to chlorine. We'll have to look up the bond energy for chlorine bound to chlorine and only multiply by 1. So we'll have to get that information. That will be the total bond energy of the reactants. And subtract that from the bond energy of the products. So you have to be careful about the bond energy of the products here. Look at this molecule. So what I can see is I see 4 bonds forming to make CH3Cl. 3 of the bonds are carbon-hydrogen bonds, and 1 of the bonds is a carbon-chlorine bond. So I'm going to have to look up 3 carbon-hydrogen bonds and 1 carbon-chlorine bond. Now, that's not the only thing I need to look up. And so the other product is HCl. We have 1 of those. And so I'm going to have to look up 1 HCl bond. So I have 1 of these of chlorine-chlorine as well. Okay, so let's go ahead and look up these values. And so if you're given a test, you will be given a table of bond energies. And so what you can see there, the table is, I have a listing of the bonds, and then I have a listing of the energies. And so it's not in that table called bond energy, it's called BDE, or bond dissociation energy. It's exactly the same thing. Okay, so let's look at the table and see what the carbon-hydrogen bond energy is. So the carbon-hydrogen bond energy that I see in the table is 415 kilojoules per mole. So I'm going to leave out that unit. And so you're going to have to multiply that by 4. Now we're going to have to look up the bond energy for diatomic chlorine with a single bond. It's 243. Now let's look at the products. Let's look up the carbon-hydrogen bond energy again. And so you can see it's basically what it was before, it's 415, but we need 3 of these. And then we need one diatomic chlorine bond. Be careful here. It's carbon to chlorine, right? Carbon to chlorine, not chlorine, chlorine, carbon to chlorine. So we look up a carbon to chlorine bond, and so what I see is 330. Now we need one more bond, HCl, so I'm looking at the table, and I see 432. Okay, so you're gonna have to try this on your own. I want you to go ahead and multiply 4 times 415 plus 243, and you'll get some number here. And then you're going to have to multiply 3 times 415, added to 330, added to 432, and you'll get some number here. And in the end, the answer should be negative 104 kilojoules. And so what does this mean? It means that when you carry out this reaction, it has a change of enthalpy for this reaction is negative 104 kilojoules. The negative sign indicates that this reaction is exothermic. It's releasing heat into the environment. And so 104 is a moderate value. And so what you can basically see is that we have calculated this value not by an experiment or using some of the other techniques we've done. We've just used it by looking solely at a table of bond energies. And so that's sort of the power of tables of bond energies, is that you can rapidly get a good estimate as to what the change of the enthalpy for reaction is. Okay, so moving on to one more thing I need to talk about. So I'm going to bring up this slide here. Okay, so you need to know the relationship between how the atoms are bonded together and the length of the bond. And so what I think you can sort of see in this table is that as you increase the number of bonds between two of the same atoms, or maybe two different atoms, that the length of the bond decreases. So look at this first red box here. And so what you can sort of see is as you go from a carbon, single bonded to carbon, to a double bonded to carbon to triple, what happens is the length of the bond decreases. And so as you increase the number of bonds, you bring in the atoms closer and closer together. It doesn't really matter what kind of atoms that you have, that always is true. So with the next series, we have carbon and nitrogen, and the same thing happens. If you increase the number of bonds between carbon and nitrogen, the length of those bonds decreases, bringing the atoms, the carbon and nitrogen atoms, closer and closer to one another. And if you can also look at that series there of nitrogen, same deal. When you increase the number of bonds in between the two nitrogen atoms, the distance between those two nitrogen atoms decreases. And just note that these distances here are very small. They're in picometers, but they are measurable. And again, the key thing to know is that as you increase the number of bonds between these atoms, the distance between the atoms decreases, is because the bonds get shorter and shorter. Okay, well, thank you for listening to that, and we will see you next time.